trial. Is that
Yes,
right?
sir. No.
Okay, good. Okay, so this is a uh, uh, another article I wrote, and it's another thing on cognitive, computational cognitive neuroscience of lies and truth and lies. And one of the things that we have come to understand very well is how human natural language uh, is computed in that uniquely by humans. So you can't do studies of mice or cats or pigs or anything, and because they don't speak anything even approaching, they don't communicate in ways that are even approaching how humans can communicate through their natural language. And we know pretty well that sometime 50,000 years ago to 200,000 years ago, probably closer to 50,000, uh, Homo sapiens, us, evolved to have natural language. And it was very rapid. It was a very rapid evolution. And it was a revolution, an evolution of a part of the brain. And so if you're a right-handed person, it's in the left side of your brain above your ear and close to your eyes, which is interesting, but it's above your ear, which uh, is where things like the trigeminal nerve comes to, which controls your lower jaw and tongue for speaking. And it's also near your ear for hearing. If you're left-handed, it's probably that same organ that's been developed inside the brain is on your right side, not the left side of the brain. So if you are a right-handed person, it's almost certainly on the left side. If you're a left-handed person, it's like there's a 50% or something probability it's on the right side. But generally speaking, it's on the left side of your brain. And the two sort of well-known areas that evolved very, very quickly was something called the Wernicke area, which is the one that interprets language, the one that recognizes what somebody's saying, and Broca's, which is the one that produces speech. So when you talk, Broca's area is the one that's responsible for your ability to talk. And when you hear somebody, Wernicke's area is the one that gives you the ability to understand what they're saying. And Broca's and Wernicke's are next to each other. So there's another little area, I forgot the name of it, that's sort of the interface between your speaking and listening. And we think the Broca-Wernicke area and the little in between area is what you saw with ChatGPT when all they were doing was predicting the next word that would be said. And in other words, if it was speaking, it would just predict the next word. And if it was listening, it would just understand in terms of the next words that were actually occurring. It would alter the recognition network. And so it didn't use the rest. ChatGPT did not use what in humans is called the frontal cortex, which is where logic, where your reasoning happens in a very special way. The whole brain knows how to reason, but careful reasoning and stuff is heavily frontal, but it's not in the speech areas. So speech areas are, or the natural language areas, um, so when ChatGPT succeeded, we expected it because the intelligence is actually built into just listening and talking, even if you're, because the language itself builds in the apparent, uh, the apparent intelligence, even though it's not the kind of deep intelligence that a human can can bring to what he's saying and hearing. At the same time, a human being can hear and talk with no more intelligence than ChatGPT had in its first versions. Okay. So this is uh, so what this is this article is on how um, natural language actually works and why it could evolve so quickly, because uh, it evolved in a few tens of thousands of years. Um, Probably, in my opinion, probably about 50,000, 60,000 years ago. Um, and once it had evolved and it kind of stabilized, the um, uh, the human population conquered the world, basically spread over the world, and we have what we have today. Okay. The uh, so how could it evolve so quickly? And the answer is in this article. So um, the basic thing the article is trying to say is that knowledge in the brain is, even though uh, everybody knows what a hierarchy is, you know, they're colors, and then each there, and then underneath that you can list the different colors that there are. You can talk about a city and the streets in the city and the cars on the streets, and those are all hierarchies. But the knowledge in the brain is we've known for years, and um, this is because we were looking for hierarchies, and when we were looking to see knowledge in human brains, memory essentially, what people knew, we could never find the hierarchies. That knowledge does not appear to be hierarchically intrinsically organized. It appears to be responsive, but it's not intrinsically hierarchically organized except in certain ways that are uh, kind of obvious when you talk about them. And I'll talk about them in a second. So this is sort of a hierarchy to them. But when you uh, move your hand, for example, or pick up a pencil with your hand, there's the knowledge of how to pick up the paper with your hand is a formation of a hierarchy of control that's dynamic, and it is a hierarchy from the decision to pick up the pencil, top of the hierarchy, to picking up the pencil, and your brain and you becoming aware that you did it. You succeeded in picking up the pencil. And that is dynamically hierarchically organized. And if you look at natural language, every natural language spoken by humans, something called the surface structure of a sentence uh, is completely hierarchically organized always. So one of the sort of questions that I'll have here in a second is whether or not you were taught in school to graph sentences. So you'd have to say, well, this is the subject of the sentence, and this is the predicate, And then in the predicate, you've got the verb and the object, that kind of stuff. I'm curious if people, if everybody's been taught that in school. I know I was taught that in high school. And it turns out that if they teach it in the school, everybody can do it. In other words, teaching that is not hard because when you're taught, when you're shown how to create a hierarchical graph of a sentence, it's just, then you can do it, and you can do it on any sentence. That's a very profound thing. Because people don't do things easily that they don't already kind of do. Okay. Sometimes they have to be shown how to express it, which is what the teacher does when they show you how to graph it. But these are hierarchies. They're strict hierarchies. Another thing that we know about every natural language spoken by man is that there are always sentences, and the sentences can always be hierarchically organized. And the sentences in a story, in a narrative, for example, are always hierarchically organized. The sentences are hierarchically organized. This is crazy. So there's a hierarchicalization of the knowledge in your brain when you say a sentence in order to say it, in order to produce a series of words that express that concept. Just like when you decide to pick up a pencil, your brain computes a series of actions that are necessary to hierarchically series of actions hierarchically organized in order to be able to pick up that pencil and know you'd picked it up. Okay. And so the argument is that for example, the motor area of the brain, which is if you put your hand on the top of your head from ear to ear, on the top of your head, that's your motor cortex. And that's a hierarchicalization engine and de-hierarchicalization engine. Okay. And we know that. And so we see these systems in the brain that know how to serialize the activity of the neurons, the rest of the neurons in your body, okay, and deserialize your senses into things that you can express as sentences or whatever. And so what we think these language areas are doing is they're just simply performing the hierarchicalization or the serialization, deserialization of brain knowledge, but they do it from knowledge from almost any part of the brain, which is crazy. So they can talk about what you see, which is what happens in the visual cortex, which is if you hold your hand in the back of your head, your hand is going over the visual cortex of your brain, and you can talk about it. You can also talk about what you say, which basically means that this serialization, deserialization stuff is able to serialize or deserialize the information in what you say in natural language. So you can talk about language. And out of that comes crazy things like the fact that dictionaries exist, that that any word can be defined as in other words, in other words. That's what a dictionary is. And that's a very special thing, and from a computational point of view. So we see how this works, and so the argument is whether or not y'all believe this statement that natural language is simply hierarchical serialization and deserialization of brain information. It is not inherently hierarchically serialized. In other words, that's the argument that's made. And, uh, as they say, I'm an expert on this. And there is, I don't know how many scientists like me in the world that believe this, but um, it'll be on the order of, of 200 or 400 or something, number like that in the world, um, of which I know some of them. And they all uh, have seen the evidence that I've seen over the years. And they would all say the same thing, pretty much. Although you can choose to believe me or not. But the argument I'm making, I think, is so the critical element of the thing for you to accept it is that you can graph a sentence. And when you graph the surface structure of the sentence, the words themselves, you graph them into a hierarchy, and the hierarchy you graph and the hierarchy somebody else graphs are the same hierarchy. Now there'll be some cases where you put the parentheses, you divide it up slightly differently for various reasons everybody sort of seen, but by and large everybody will agree. And then if there is a disagreement, they'll just sort of agree to, for example, if you have a two uh, a connector between two clauses like and or they're both clauses or sentences, then how you choose to organize those two clauses into a single hierarchy. Um, there's a little bit of flexibility there, but not much. And then the two people can agree this is how we should do it, and then from then on out they'll do it that way, and they never did have a problem doing it. So that's the critical thing. If you believe that is the way that you can do that with any sentence, then we basically made our case, because that's telling us something that everybody can directly observe. It's a scientific observation, and it's really hard to explain that in anything other than that's how the brain is computing sentences. And so that's sort of the argument. And so and the thing that I'm sort of curious about is I know my wife was never taught how to graph sentences. So she went to school in Long Island, out on the island in the countryside. And apparently her school, they didn't teach kids how to graph sentences. So she says that she doesn't know this. And so now all of a sudden I'm sitting here going, well, I thought everybody knew this. And so now I'm wondering whether um, there are other people don't believe it or don't know what I'm talking about or whatever. So I'll be really interested to find out what it is. So my argument is there's is it the truth? The answer is yes. And I'm there's a lot of detail. I've given you some of it, which is that there are existing brain areas that. So what we think is this because the the deserialization of perception, like with eyes, deserializing the series of events that you can see into a visual perception. So if you're looking at a pencil, You see it no matter where it is in the visual field. The that that de that deserialization of the events happening to the neurons in your eyes through the brain deserialization process says, I got a pencil here. Um, and the serialization process, which is you draw a picture of a pencil, okay, with your motor action, or you pick up a pencil. The uh, that those kinds of actions, that kind of processing in the brain, is fundamental and is probably on the order of 500 million years old, since we think that brains are about 500 million years old. And pretty much you could be, now there may be 100 million years. We don't really know. But these fundamental capabilities of doing, of brains remembering things and then being able to serialize or deserialize, serialize behaviors out of them, in other words, be able to control motions and affect the world out of them, and then being able to perceive objects in the world, which is deserialization. All are all hierarchicalizations of the knowledge that is fundamentally not hierarchical in the brain. It's just not organized that way. And the I don't want to go into. I don't want to go too deep. The and so because language is just another instance of neurons already knowing how to serialize and deserialize, but now on auditory input and verbal production, principally through the tongue and the lower jaw, by the way, and the neck, which is the trigeminal nerve. That's where this stuff came from. And then because natural language came out of that, and it can do that serialization, deserialization on anything that's going on in the brain. So you can report on what you see, what your eyes see, in the sense of I see green or I see an edge here, as well as I see a pencil. Okay. So the whole idea is that that the reason it happened so quick, natural language happened so quick, was that the fundamental computation that's needed for language was basically already there for a lot of other things. And so these are just neurons doing what neurons do, and they've been doing it for, let's say, 100 million years. And so very, very minor changes in your DNA or additions to the DNA or whatever created natural language, but it's still the same brain. It's largely still the same brain. And so this is where you get claims like dogs can think too, and they're conscious, okay? Because the argument is it just doesn't make sense from an evolutionary point of view, what we've observed, if they couldn't think like we think, which is weird. Now when I say that, they think like we think computationally, whereas they think, and they are argument to be conscious. These are not, anything other than scientific things. So is the whole truth, as far as it goes, this is the whole truth. You can actually, if you don't have to study neurology, you don't have to study neurons, you can find all of the evidence for this claim in deep studies of linguistics. So you can actually, if you get trained in what is called structural linguistics, it takes years to learn. And this is a stuff that's got a huge literature. Um, these are people who've been studying, um, and it's also called theoretical linguistics. But de Saussure is the guy that started this activity back in 1902 or something. Um, and he was the first guy to actually uh, develop linguistics as a scientific effort. Um, and he did notice the hierarchicalization stuff. Um, is it nothing but the truth? And I said, yeah, I don't know anything other than it's nothing but the truth. What's the deceit? I said, there's no deceit. It's just informative. It was intended to be the truth. Uh, I'm the one who believes it's the truth, so I'm going to say it's the truth, and it came out of my brain. So after 50 years worth of work, um, what's the motivation behind the truth or the lie? It's just to be informative. I think once you begin to understand how the brain computes, your respect for what the brain, for what anybody's brain can do, goes through the roof. It just what our brains do is un is one of the most amazing things in nature. It's just stunning the computation that brains can do in very, very short periods of time. Coordinated computations, just amazing. What's the social acceptability? Again, I'm a scientist, so if I believe something scientifically, um, I'm being a scientist, believe that it's acceptable to talk about it, and I'm useless otherwise. I'm a totally useless human being other than that. So what label would improve the social acceptability of the truth or the lie? I actually did what I did last week, which is I think that a label that says this is true, and then somebody was joking that, well, the problem is that me saying that putting that this is true on a label on this, somebody immediately gets suspicious as to whether or not I'm lying, which is which is okay. So that's the sort of uh, thing, and what I want to do is uh, go and I'm going to do. Oh, I'm going to go back to the here just a second. Stop share. Okay. So what I want to do is uh, go through the jurors and give a 20-second, 30-second summary of your verdict. And I saw a lot of people who just didn't know. Okay. And but I'm really asking a question that most of y'all would know or not know, which is, were you taught graphing sentences when you were in school? And did you find it easy? And if I'd love to know whether you did or didn't. And if you did, because I've got at least one example, which is my wife, who was never taught it. And, I had to show her what it was. And she picked it up immediately, but it was phenomenal. I thought that they didn't teach it. So, juror one.
Yes, I'm here.
So, could you give me a summary of what your verdict was, like a 20 or 30 second?
No problem, sir. I would just say that I agree with the plaintiff or with you in this case. I find this perspective on the brain and natural language very interesting. I'm not an expert on the topic, but I do think this argument provides a compelling way to understand how the brain processes language. It has also sparked an interest in me about learning more of more or about learning about neuroscience and linguistics intersect, how they work with one another.
So
Um,
I'm gonna put in chat. I'm just hoping I can do this. I'm gonna put in chat a name of a guy. Okay, and
yes, sir.
his name is Sosnowski. His first name is Terrence, but I have to spell the name, and I'm going to try to put this in chat if I can see how to do it. Okay, so he wrote a book, and the book is Deep Learning Revolution. So it's, and I'm probably misspelling his first name, but the last name I've got right is Sosnowski. It's Terrence. I think it's Terrence. Now that I look at it, but it's Sosnowski, and the name of the book is Deep Learning Revolution. And Terrence, uh, to, so he's retired now. He's like me, um, but he is probably in my world. He's one of the most famous people. To give you an idea of how respected he was in neuroscience and neuroscience.
Mhm.
He was the editor in chief of the top two journals in neuroscience for like 20 years.
Wow, that's impressive.
Yeah. And so Terrence, so he was funded um, when he was a kid. So he was funded when he was like 30, 33 years old or something. So he got his PhD at the University of Maryland, but he was funded by the Hughes Foundation, and most people don't know about this funding thing. They uh, uh, Howard Hughes uh, left a big amount of money to fund uh, uh, essentially uh, Howard Hughes scholars or whatever you want to call them, researchers or something. And the uh, what the funding did was it set you up for life. So if you receive one of these grants from the Hughes Foundation, there are very few of them that have ever been given. You're set up with some number of millions of dollars a year.
Wow.
And so Terrence had 60 people working for him at the University of San Diego. I forgot it was at UCSD, but it was a building. It's a building that was given to him as part of the Hughes thing, a multi-story building on the edge of the Pacific Ocean. And he hired the brightest people in the world to work on these problems, the very problems we've just been talking about. And he wrote a book. And the book is for anybody to read. It's a great book, doesn't have any fancy words in it. And he explains um, what the state of things was in around 2018 or 2019. That's when he wrote his book. And then he retired. Uh, and but the organization that he's got has continued. So the that building is still in operation, and the people are still doing good work, and so forth and so on. But if that book, if you can find it, which should be easy to find, I think you can get it in Audible and listen to it. Um, is a worthwhile, and it comes in Kindle. And I know Terrence didn't care about making any money off the book, so I think it's cheap. Um, I, I, I think I got the Kindle or something. I can't remember what I got. But that book,
I'll definitely look it up, sir.
yeah, and then you can have fun with that book because that's really one of the top people telling you um, uh, how all this gives you the full history. Um, uh, and this was his swan song. This was his telling everybody in the world, "This is what I've learned." Okay, which is a great book. So Juror two.
Hi, my name's Julie, and I also wanted to answer your question by saying we didn't graph sentences when I was in high school, so
Oh,
I'm not too familiar with that.
wow. Okay. I mean,
Yeah,
this is what I'm hearing. I mean, this is crazy. I didn't know. Because when you're in high school, you only know you're in high school, right? So
yeah,
how would I ever know?
yeah. I was a little bit confused because I've never heard of that before, and I got out of high school last year, and we were not taught that at all.
Yeah, I was told by somebody else who said that they're not taught graphing. I was taught graphing in English in the English class.
Okay.
So it wasn't the English language, it was the English literature class.
I
Yeah.
must be from old school because I was taught it as well, Bob, whenever
Yeah.
I was in high school.
I think you can look it up and you can see in some of the papers I've written, I actually I I don't draw the graphs, but I show you how you parse a surface structure. And there's a lot of instances that you should be able to find it on the internet easy enough. I mean, I don't know where to look for it, but I'm sure it's there.
You probably look on like most go to like type in your search engine bar, graphing sentences, and it should pull up
Yeah,
that.
it should just do it. And then once you see how to do it, you that part of it, I think, is true, which is once you
Fundamental.
see how to do it, it's really easy to do.
Yeah.
So, but yeah, I, yeah. So this is really interesting, Jur too. So, Jura three.
Hello. So, what I've learned basically is that the human brain uses old brain circuits to understand and speak languages. But then I would also like to add that there is still a lot that we don't fully understand as and I think I speak for myself and many others as well. We are not very much educated on the brain specifically. And then to add to your question, yes, I've learned graphing in school,
Huh.
but we don't, or yes, we don't know it as graphing. We know it as sentence structure.
Yeah, that's right.
Yes.
That's another word for it. I don't know how I I'm very bad at remembering names for things, and so
So, yes, you actually learn, well, where I'm from, we actually learn, and I've taught it as well. We learn that from primary school already
yeah,
through high school.
yeah, and I think I kind of learned it in primary too, but I don't remember that expressly, but I do remember learning it in English class and in high school.
Yes. So,
And I can't remember whether I already knew something about it. I can't remember any of that. So, but it's really interesting. So you learned it in elementary. That's
yes,
exactly what I would expect is that a
basically from
9 year
grade
old or a
four,
10 year old,
five.
a 9 or 10 year old can do it. It should be. Um, the so uh, the uh, what I didn't mention earlier, and I forgot to mention it, was uh, one of the so if one of the so I used to code natural language understanding system. So I was one of the guys that wrote some of the early natural language understanding systems. In fact, um, uh, uh, some of the search engines uh, uh, used my code because I could parse all the sentences on a web page, and I would parse them as surface structures. Writing a program that could do the surface structure parsing is really easy. This is crazy, because normally when we try to write a program that can do something that people can do, it's really hard. But so the original code that I wrote got licensed by, you name it, Microsoft, Google, all these other guys. I never made any money, but they paid me the $100 or whatever it was, and and what I would do is they would run a test. They would give me a bunch of text, and I would parse all the sentences in the text and do it in 2 seconds for a page. And they would always say, "You've got the best parsing system we've ever seen." Okay, and all I was doing was seeing if it was easy to parse. And sure enough, it is easy to parse if you just write the code. So every word you have to know whether it's a noun, verb, or adjective or whatever. You have to know its grammatical class. So you've got a little dictionary that looks up for every word the different grammatical classes that word could belong to, and then you build something called an augmented transition network, which is a Markov process for y'all who know Markov, a Markov processor, and it just makes short work of perfectly parsing surface structures. And it's completely believable that the brain knows how to do that exactly that way. So, but now once you go beyond that and you try to figure out what the sentence means, it gets really hard fast. But parsing the sentence and breaking it up into phrases is very straightforward. So, juror 4.
Hi, good evening, sir. Good evening, all. First and foremost, wow, I'm so fascinated with all the information, and I totally agree with you. So I can also state that on high school we did the brain, but there was only limited information provided. So as I'm listening to you, it's like wow, wow, wow. It's just amazing.
It really is. I mean, yeah, just as you understand what happens between your ears, you will get. There's nothing more awe-inspiring
Yes, yes.
than what's happening between your ears. It's just unbelievably.
Yes,
Everybody thinks brains are just globs. They're not. They're incredibly
it is.
incredible computation engines.
Oh, truly.
So juror 5.
I don't see anybody in the chat saying they're 5 or in the.
Juror 6.
I don't have a 6 either.
Okay. Juror 7.
Hi, yes, I'm juror 7.
So could you summarize
Hi.
your?
I was okay. So firstly, just to say, I also learned how to graph sentences from as early as obviously elementary school there in the States, but yeah, it's obviously around grade 4, around
Wow.
4th grade,
Wow.
right through to high school. So it's a skill that you obviously learned a lot sooner
Yeah.
than people in other places,
Yep.
which I'm starting to realize maybe it's not something that is taught as widely as I had thought it was. Some days just a basic thing that everyone should be taught and know from a young age.
Yeah.
I am still slightly confused on the whole topic of this call. I didn't really understand when I read the article. I watched the video, and I still didn't fully grasp the concept of what we were talking about, but more, and it's quite interesting to know more about what goes on in between our two ears from just everything, every sentence, every word that comes out of our mouth, every thought, all that I would just passes through, and the computer that is the brain, how it analyzes everything and brings everything together towards a certain point. Yeah.
Yeah, I think that uh, the part of the, and I think I say this in the paper, is there are 100 billion neurons between your ears, and each neuron has about 3,000 connections on average to other neurons. And each of these connections, so this is like in the trillions, 300 trillion connections between your ears. Each of the connections. So one thing that people don't know, and uh, is neurons are incredibly small. They're, skin cells are bigger than neurons. But this is insane. Even though a neuron can be 3 feet long, okay, seeing a single neuron fiber is really hard, even with a microscope. And so so these are really uh, there's a huge number of these things, and they're computing basically all the time. If you're awake, they're computing all the time, and they're all computing in completely organized ways and so forth. And that's the and it's all in parallel. That's the reason that but Jeffrey Hinton, who's one of the people that are just like me, that same kind of background, um, he calls the brain an intuition engine. We can figure what the brain computes is what we call what anybody would call just intuition. Yeah, I can lift my hand. Here, I'll show you. Okay. I had the intuition I could lift my hand, and I just did it. Okay. The we're not logic engines. Logic comes now. The computation that's done for intuition is capable of doing logic. We've known this for like 20, 30 years now. So we can take these same engines and turn them into completely logic engines, so they can do deductive calculus or whatever. But so you can do it, but these engines really slow down when they're doing that kind of stuff. And the human brain does the same thing, which is it's a lot more work for the human brain to reason than it is to just intuitively say this is true or this is a lie. Okay. And when it sees something that it thinks is true and or it thinks is a lie, it's largely right. But what's the reason it's an intuition engine and not a logic engine is logic engines take time, and often in the 100 million years worth of animal evolution, taking too long to jump to the next branch, you were dead. And so you had to make up your mind as to whether or not that was really a bear. Okay. And you didn't have a lot of time. And so what that did from a long-term evolutionary point of view is it made the brains, even though they're capable of reasoning using intuition, they getting things understanding the truth by proving it to yourself that it's the truth is really hard, and it just takes time, and we don't preferentially we don't have the time to do the reason, which is the reason that people like me exist as scientists, because we spent the years doing the actual proofs of what's true, and nobody else has time to do it. But we were fortunate to be paid or given a small salary to be able to do it. And so that's the way to think about it and Geoffrey Hinton is another good guy to read. So he's Geoffrey Hinton. He's a guy like me. So if you ever read about him, you'll see he and I had a virtually parallel educations and so forth and so on. So Juror 8.
Hi, could I'm not actually very good in anatomy, but I learn a lot about what's happening in the brain. But before, when I answer and read about the verdicts, I didn't actually really understand about the case, the natural language in your brain. So I Googled my own stuff, and I actually learned a lot. And I was also thinking this way. But I also noticed, especially with small kids, foreign kids, what I noticed, they can adapt quickly more than one language. Where the adults will struggle to learn a language, then they will quickly adapt like 1 or 2 or 3 languages.
Yeah,
that was what I observed.
Yeah, and so we don't know. I want to be careful how I say this. So we don't know. I mean, to this day, we don't know why that works that way. Okay. But it's absolutely the case that when you're a little kid, you can learn several languages. One of the things that is, and each of these languages will occupy an area in these language areas. So each one of the languages will occupy an area that you, and so in general, most people can't learn and become completely fluent in more than a couple of 3 languages. There are rare cases where people have claimed to be fluent in like 10 languages, but there's like 2,000 languages. Okay. There have been historically claims of somebody who said, I've learned 35 languages or something. And those were usually very quickly debunked by bringing in, some fluent speakers of certain languages and realizing this guy was not fluent in a lot of these languages. But but 3 or 4, your brain can handle, but each language takes up space in your brain, and there's only so much space there. And but they're using the the neural systems are perfectly general. They're the deserialization, serialization neural systems are perfectly general. They can apply to any language as long as you have the as long as your DNA tells you this is something that you want to do. Okay, you will do it. Okay, but if your DNA doesn't give you the idea to do it, then you won't do it. So what we kind of think goes on is little kids, they want to understand. They don't understand that there's English and French or whatever. Okay, they just know that grandma speaks using words that grandma uses, and ma uses words that ma uses. And from their point of view, and they'll distinguish it. You never talk to grandma using ma's language, and you never talk to ma using grandma's language or whatever. And so that's the separation that actually occurs. It's not that the language, it has to do with the same thing, that there are always synonyms in a single language, and that every word can be defined in terms of every other word. It's all part and parcel of the same fundamental mechanisms. But we don't really truly understand why, when you get older, it's so much harder to learn a second language. Another thing that we do know is that if you didn't grow up learning two languages or speaking two languages, it's much harder when you get older to learn a second language. But if you grew up with two languages, you could probably learn a third a lot easier, and a fourth to some degree, and you could pick up some other languages, some pieces of other languages. But getting upwards to 5 languages, you have to be suspicious as to whether the person is actually actively fluent in all 5 of the languages. But I think some people do exist that can do it. So, Jared 8, did that help?
Yes, it really helps. Thank you very much.
Okay, so that's about it. So I appreciate it, and
I like these trials that you do here because it helps me learn a lot about the.
I'm gonna continue to do these trials where I have Robot Love, this robot speaker that I've got narrating reading my articles.
I've been showing them off to people.
Yeah, it's a lot easier, and all the YouTubes are free and easy to get to. You know, anything in Medium, you have to sign up for Medium, but the YouTube, I can just make it free, and then all of that's completely synthesized speech. I do not edit a word he says.
I kind of like Robot Love.
It shows you the state of the art in AI now, in generative AI. And all of this is just advanced perceptrons. These things are all just using the same computational engines that I was coding in 1980, except they have hardware that we never had.
Pretty interesting.
Yeah. Okay, so we'll see y'all.
All right, bye-bye.
Bye.